So I want to tell you about a pattern I see repeatedly across deep tech startups, and it's one of the most counterintuitive things in engineering development. The companies that make the most expensive mistakes are not the ones with the weak engineering teams. They're the ones with strong engineering teams who are moving fast, who are confident in their technical approach, and who skip critical characterization work, sometimes at small scale, because they're certain they already understand the system well enough. That confidence, which has been earned through genuine expertise, is exactly what sometimes creates that blind spot. So in this video, I want to walk you through what engineering risk review actually looks like, where the most dangerous gaps tend to hide, and how experienced technical advisors catch the things that even great engineers miss. My name is Dr. Colleen Spiegel. I'm an engineer and tech advisor for deep tech companies, federal grant reviewer for NSF, DOE, and NIH. So the assumption that most founders and investors make is that a technical risk is primarily a function of team quality. Strong team equals low risk. Weak team equals high risk. This is definitely partially true, but it misses something important. Technical risk is not just a function of how good your engineers are. It's a function of what your engineers know that they do not know, like what they can admit their weaknesses are versus what they do not know, what they for certain know that they do not know, basically. The first category is known unknowns is manageable. Your team identifies the open questions, the design of experiments to answer them, and tracks progress against those experiments. This is standard engineering practice, and good teams do this very well. The second category is unknown unknowns, where this is where million-dollar mistakes can live. So I'll give you a specific example from my pharmaceutical manufacturing days, and this illustrates it perfectly. A formulation development team was working on a new drug product. The team was excellent. They had very deep expertise in chemistry. They understood the active ingredient, and they had a formulation that performed well at the lab scale. But what they didn't characterize adequately, because they were confident in the formulation, were the physical properties of the material under the conditions they would experience during scale up. So for example, viscosity at different temperatures, different shear rates, behavior during thermal cycling, sensitivity to mixing time and speeds, the way that that material responded to the mechanical stresses of manufacturing equipment, operating at the production speeds. At the lab scale, none of these issues were visible. The batch sizes were small enough that mixing was uniform, the temperatures were easy to control, the shear forces were negligible at that scale. But when you scale it up to the manufacturing scale, all of those mattered, and several caused failures that required months of investigations and reformulation work. So the team wasn't incompetent whatsoever. The team was excellent, but they simply did not know what they did not know about how their formulation would behave outside the conditions that they characterized. So in my experience with reviewing technical programs for deep tech startups and federal agencies, is that there's hidden engineering risks, and they tend to fall into several consistent categories. So the first one is inefficient small-scale characterization. This is the pharmaceutical example I just described, and it applies across industries. The pressure to move quickly means teams sometimes will skip characterization experiments that they feel that are redundant or obvious. Things like viscosity measurements, thermal cycling studies, stability testing under stressful conditions, rheological characterization, material behavior at boundaries at the operating windows. Some of these experiments sometimes feel unnecessary when you're confident in the system, especially when you've worked maybe with similar types of formulations. But after experiencing any type of scale-up failure, they felt like those were probably essential and would probably be, have caused minimum time and resources to execute. So the rule that I apply is if you cannot describe how your material or system behaves at the extremes of every relevant operating parameter, then you have not characterized it sufficiently for scale up. There's also interface and integration risks. So deep tech systems are almost always multi-component. There's multiple materials, multiple subsystems, multiple interfaces, and the individual components may be very well characterized, but sometimes how those interactions are or the interfaces between them might not be very well characterized. So for example, how does the membrane behave in contact with the electrode over thousands of hours? How does the seal material respond to the thermal cycling the stack experiences? How does the catalyst layer change when the field geometry changes? Interface failures are particularly dangerous because they often do not manifest until the system has been running for an extended period of time. And then by that time, there's been a significant investment in time and resources that have already been made. So the third item is scale-dependent phenomena. So there's many physical phenomena that are negligible at small scales, and they do become significant at larger scales. It could be the heat transfer. Sometimes, on larger scales, the heat transfer is not as even, maybe because of vessel design or other factors. Mass transfer, mixing uniformity, different types of impellers and so forth can change the mixing and can change the final product. Residence time distributions, pressure drops, gravitational effects on fluid behavior. So a process that's really well controlled in the lab scale, like for example, at a 1 liter of volume, may behave completely differently at 1,000 liters. And not because anything was done incorrectly, but because the physics changed the scale of the system. So another category is assumption inheritance. Technical problems often inherit assumptions from previous work, especially if products or formulations are similar. So they make the rationale that the behavior should be similar. And sometimes this could be from academic literature, sometimes from previous projects, sometimes just from supplier data sheets. But without verifying some of those assumptions that apply to their specific system, um, under their specific conditions, things might go awry. So a material specification from a supplier was validated at different conditions than yours. A processing parameter from the literature reference was established with different formulation. Let's say a performance model was built from different geometry. So assumption inheritance is invisible unless someone specifically traces every critical parameter back to its source and asks what was actually validated for our specific case. So what does an engineering risk review actually look at? So an engineering risk review is a structured process for identifying unknown unknowns before they become expensive failures. I'll walk you through what this actually involves. So the first step is technical program mapping. So we'll first map the complete technical program, every major subsystem, every major material, every key process parameter, and its interface. So this is not a summary review, it's a detailed technical inventory of your product and process. And for each item in the inventory, the question is, what do we know? What have we validated? What are we assuming? And what have we not yet tested? And can we make very good assumptions and rationale to not test it then? Step 2 is the characterization gap analysis. For each critical material and process parameter, has the behavior been characterized across the full operating range? Not just at the normal operating points, at the edges, at the extremes, under stress conditions, under worst case scenarios. In pharmaceutical development, this means characterizing viscosity across the full temperature range of the process, not just at the target temperatures. This is very critical, right, for highly viscous formulations, emulsions, some sort of suspensions. And then there's also thermal cycling across the number of cycles that the product will experience in its lifetime. So there's mixing behavior at scale and speed of manufacturing equipment, not just lab equipment. So the gaps in these types of characterization studies is where the risk can live. Step 3 is the scale-up assumption audit. So for every assumption in the technical program, where did it come from? Was it validated at the current scale or inherited from a different scale, or a different formulation or different geometry? Every inherited assumption has not been independently validated for the current system at risk. Step 4 is interface and integration review. So for every interface between subsystems or components, What is the failure mode? Has it been tested? Under what conditions? For how long? Interfaces that have not been tested under representative conditions are risks. So step 5 is risk prioritization. Not all risks are equal. The output of an engineering risk review is just a list of gaps. Um, it's basically a prioritized risk register with recommended mitigation actions. So which risks, if they materialize, would be catastrophic versus manageable or even almost negligible? And which could be mitigated with targeted experiments? Which would require design changes? This prioritization is where experienced engineering judgment is the most valuable, and it's knowing which risks matter enough to address before the next funding milestone versus which could be monitored. So engineering risk reviews are very valuable at 3 specific points in deep tech and startups development. So of course, the first one is before a scale-up decision. Before you commit resources to a pilot plant or manufacturing line, a systematic review of your technical program can identify the gaps that could cause failures at scale. And this is for a fraction of a cost rather than discovering them after the capital has been spent. So the other time is before a funding raise. Investors and their technical advisors will conduct their own due diligence, and a proactive engineering risk review gives you the opportunity to identify and address these issues that they might find before the diligence process starts. So going into due diligence with a documented risk register and mitigation plan demonstrates technical rigor. And coming in with those gaps that the investor's advisor might identify could raise questions about what else you might have missed. And another stage where this is important is before a critical regulatory submission. So for medical devices, pharmaceuticals, and other regulated products, regulatory submissions require evidence of process understanding and control. A systematic risk review ensures that evidence exists and is documented before the submission, rather than being identified as a deficiency during that review. So great engineering teams can make expensive mistakes, not because they're not good engineers, but because the things that create scale-up failures are often invisible at the scale where the team has been working. So a structured engineering risk review makes that invisible visible before it can become very expensive. So if you're approaching a scale-up decision, a funding raise, or a regulatory submission and want an independent technical review of your program, I offer engineering risk assessments for deep tech companies at semcio.com. The link is in the description. Subscribe for the next video in this series. We're covering how to evaluate whether your prototype is actually ready for manufacturing and the specific gaps that founders consistently overestimate. My name is Dr. Colleen Spiegel, and I'll see you in the next video.